Today we're going to talk about how to find different probability. So in this first example we have a 52 deck of cards, a standard deck, and so what we want to do is find the probability of drawing an ace and then a king if we don't replace it. So we're going to do this once without replacement, and then we are going to replace it in the next one. Now when we don't replace something, then that is a dependent event, because if I don't replace it, then I have one less of whatever it is left in the pot, which is going to change my chances of getting something else. So for this one, what I'm going to do is figure out the probability of getting an ace, which is 4 out of 52. And if I draw an ace card, then there's only 51 cards left. So my denominator is 51, and there are 4 kings in a deck. So I have 4 out of 52 times 4 out of 51, which is 4 out of 663. Now the reason I multiply here is because I have dependent and independent events. So I'm going to multiply them. Another way to tell is that this is then, which also means and when you have and, then you have to multiply. So again, the reason this is 4 out of 52 is because there are 4 aces out of 52 cards, but after I draw that ace, there's only 51 cards left, but there are still 4 kings in the deck. So then after I punch all that in and reduce, I get 4 out of 663. Now if we find the probability with replacement, then I will have 4 out of 52 cards for an ace, and since I put it back, I still have 52 cards, and this time there are 4 kings. The probability of that, after you reduce, is 1 out of 169. So let's do another one. Let's say we want to find getting 2 hearts in a row. 2 hearts in a row. Alright, if we do it the first time without replacement, then I find that there are 13 out of 52 cards. And since I'm not replacing it, now there are only 51 cards, and there are only 12 hearts left. Because I already took out 1 heart from here, so instead of 13, there are 12 hearts left. And since I had 52 cards, now I only have 51, since I'm not putting it back. And that probability, after you reduce, is 1 out of 17. Now the probability, if you replace it, that's going to be 13 out of 52. And since I put it back, it's still 13 out of 52, which after reducing gives you 1 out of 16. Let's do another one. Let's say we want the probability of getting a king of diamonds and then a king of clubs. Well, without replacement, there's only 1 king of diamonds in the whole deck. So that's 1 out of 52. But now, since I took out that king of diamonds, there are only 51 cards in the deck, and there's only 1 king of clubs. So that gives me 1 out of 2,652. So I have a chance, but it's a pretty small chance. If we do this with replacement, then I have a 1 out of 52 chance, and since I put it back, I still have 52 cards in the deck, and there is 1 king of clubs. So that gives me 1 out of 2,704. So my chances are better if I don't put the card back, as you can tell here. Let's do one more. Let's say we're looking for a king or a red card. You'll notice this one is an or. That means that we are going to have inclusive or exclusive events. Okay, so the probability of getting a king is 4 out of 52. The probability of getting a red card is 26 out of 52, because half of the deck is red. However, it is possible to get a red king. The red cards are the hearts and the diamonds, and there is a king of hearts and a king of diamonds. So there are 2 cards out of the 52 that are a red king. The reason I care about that is because I need to subtract that overlap. And because we have that overlap, because both of these things can happen, I can have a king and a red card and a red king card. This is an inclusive event because we're including both of the events happening. However, I need to subtract that overlap so I don't count it twice. So I'm going to add this 4 out of 52 for the probability of drawing a king, plus 26 out of 52, and then subtract the overlap of 2 out of 52. Again, the reason we do this is because this is an OR statement, so it's inclusive or exclusive, but the reason it's inclusive is because you can have a red king. And when I do that, 4 plus 26 is 30, minus 2 is 28 out of 52, and after you reduce that, you get 7 out of 13. Let's do an example of another one like this, but we're going to do it with numbers this time. So let's say we have the numbers 1 through 14. I'm going to list them all out here. (1 through 14). We want to find the probability of getting a prime number or a multiple of 4. You'll see that this is an OR statement, which means I'm going to have to add. What I want to do is find all the prime numbers. Well, 1 is a prime number, 2 is a prime number, 3 is, 4 is not, because it is divisible by something other than 1 in itself. 5 is a prime number, 6 is not, because 2 and 3 go into it. 7 is a prime number, 8 is not. 9 is not, because 3 times 3 is 9. 10 is not. 11 is. 12 is not. 13 is. And 14 is not. So my prime numbers, I have 1, 2, 3, 4, 5, 6, 7 prime numbers out of a total of 1, 2, 3, 4, 14 numbers. So I have 7 out of 14 plus, now I have to count all the multiples of 3. Or sorry, of 4. Well, this is a multiple of 4, this is, and this is, so that means I have 3 out of 14 numbers that are multiples of 4, which gives me 10 out of 14, which reduces to 5 out of 7. Let's say we want the probability of getting a multiple of 2 or a multiple of 3. I'm going to do this one in a different color. So my multiples of 2 here are 2, 4, 6, 8, 10, 12, and 14. And that is 1, 2, 3, 4, 5, 6, 7 numbers out of 14. And again, we have an OR, which means I'm going to add these now. Now my multiples of 3 are 3, 6, 9, and 12. That's 4 numbers. So I have 4 numbers out of 14 that are multiples of 3. However, you'll see here that I circled the 6 twice and the 12 twice. So in a sense, I've already counted them twice, and I don't want to do that, so I have to subtract that overlap of 2 numbers out of 14. Now, because of this, we know we have mutually inclusive events. Over here in this first one, these were exclusive because it was either prime or a multiple of 4. These are inclusive because we have a multiple of 2, a multiple of 3, and there are some numbers that belong to both. So I just subtract this overlap here, which is going to give me 9 out of 14. Those are a couple examples of how to do problems with probability.